So welcome everyone to today's seminar. Today we have the pleasure to listen to Francesca Pina from Instituto di Astrofisica in Spain. She'll be talking to us about thick disks. So to introduce Francesca, she's a Marie Curie Fellow working in the field of galaxy evolution. She leads her independent research in two different lines on the origins of stellar structures at galactic centers and large disk structures in external galaxies. She's an expert in the analysis of stellar kinematics and populations of internal structures in very nearby galaxies, mostly using integral field spectroscopy, complemented by cosmological simulation. So Francesca was previously in industry as an engineer, and then she moved on to start her scientific career with a PhD at the IAC on the chemical dynamical properties and origin of thick disks in galaxies. Then she moved on to a postdoc at the Max Planck Institute, where she joined the galactic nuclei group and expanded her knowledge to the stellar kinematic and population properties of nuclear star clusters. 1 year ago, she went back to the IAC to work on spectrophotometric decomposition and stellar populations, characterization of nuclear star clusters in the Fines and Beard survey. She has recently started her Marie Curie project called Translate, investigating dominant formation processes of nuclear structures at different spatial scales in cosmological simulations. Thank you so much, Francesca, for visiting us and presenting your work. You may start when you're ready.
Thank you very much, Anna, for the very nice and detailed introduction. So hello, everyone. Thank you very much for being here today. A big thank to is that
your screen.
Oh, that's very good. Yes. Hello, everyone, again online. I hope you can hear us again. So, yeah, thank you very much for being here today, and a big thank to Rogerio and Anna for hosting me here, for giving me this opportunity to show my work, to present my work here today to you. And I would be very happy to discuss about this work or other works today, tomorrow, and on Friday we'll still be here, and also to listen about what you're working on. So feel free to come to me and we can chat about science or whatever other topic. So today I will present my work on the origin of thick disks. I will try to show you how we can reconstruct the formation history of thick disks with the stellar populations of very nearby galaxies. And I will show you mostly results from intergalactic spectroscopy, but also I will complement at the end with some results from simulations. So let's start from the beginning, just to make sure that everybody is on the same page, because I'm not sure that everybody works on galaxies here in this audience. So let's start with the Hubble sequence, which is one of the ways we can classify galaxies according to their morphology. And we have here on the left side what we call early type galaxies, what we call late type galaxies on the right side, and from the left to the right we have like more massive galaxies on the left side, less massive galaxies on the right side, and also on the left side we tend to see galaxies with no large amounts of gas, and most of the gas is actually located in the right side of this sequence with the strong star formation and a spiral structure. And we will be talking about these kind of things throughout the talk. So I will actually take you through a journey. Through these galaxies. So we are going to talk about disks in galaxies, and therefore we need to analyze galaxies with the prominent disks, which are basically lenticular and spiral galaxies that are located here in this region of the Hubble sequence. So lenticular and spiral galaxies. And just in case somebody has no idea what a lenticular galaxy and the spiral galaxy is, so a lenticular galaxy is something like this. So with a prominent disk, but not a clear spiral structure. They are usually bright. They don't have, again, large amounts of gas and not sun formation in principle. In some cases, we have sun. And the spiral galaxies have a prominent spiral structure with most of the sun formation actually happening in the spiral structure, and also the gas and the dust. What do we know about the structure of these galaxies? And well, the full talk will be basically about a giant galaxy, so galaxies that have a disk, but we are watching them like this in the sky, because in this way we can actually analyze their vertical structure. So this is a schematic view of the Milky Way. We are actually here. The sun is here, and in this way we can actually distinguish between a bright thin structure, which is in the midplane, which is the thin disk, which is where the sun is located, where we have most of the gas, where the spiral structure is, and most of the sun formation also happens. But there is another structure which is also very important, which is thicker, which is called the thick disk, and which is like thicker and fainter, which is thought to be the envelope of the thin disk. So the term thick disk basically appeared for the first time in the late 70s, and this was a time in which the thin disks were observed already much earlier, because they are the brightest structure, and therefore everybody had observed bright thin disks in a giant galaxies. However, the concept of thick disk was something new, and for the first time, Barstein realized that it was necessary to add this second disk component when fitting vertical surface brightness profiles. So there was what we call the thin disk. This bright structure was already more or less well known, and then it was necessary to add a second structure with a different scale height, which was called the thick disk, which was thicker and fainter. So the very first definition of thick disk was actually a geometric or a morphological definition. We are going back to this in a couple of slides, because this is the definition that we also use in external galaxies in most of the cases. So a little bit later, the thick disk was also identified in the Milky Way. And in the Milky Way, it was easier to do some spectroscopy, because we can resolve individual stars, and therefore some properties were already associated to the thick disk stars. These stars appear to be very old, metal poor, and kinematically hotter. This means high velocity dispersions, especially compared to the thin disk stars. And slightly later, it was also shown that the thin disk stars are also alpha-enhanced. Then some spectroscopy was also done in external galaxies, and it was shown that similar properties was also found in external galaxies. So the general idea that we got from earlier studies was that the thick disk has to be old, metal poor, alpha-enhanced, and kinematically hot. We will discuss about this idea throughout the talk, and actually at the end of the talk, I will show you that this doesn't have to happen necessarily in all galaxies. In some galaxies that are in general young, because they are lower mass and they are located on the right side of the Hubble sequence. You remember what I explained before. We actually find relatively young thick disks. We will talk about this later, and what do these properties of the thick disk mean? Actually, we have said they are old, kinematically hot, metal poor, and alpha mass. And this actually means that the stars were from a long time ago, right? Because they are old. We don't know where. There are different possibilities, but a long time ago because they are old. And they were formed from non-enriched gas because their metallicity is low, and they are also alpha enhanced. And this means that what this suggests, one possible interpretation of the alpha enhancement, which is the most the used one for the thick disk, is that we would form them with in a fast time scale, especially compared to the thin disk. There are also other interpretations, but in principle, we will think about a fast time scale, which is connected to the different lifetime of supernova type 2, supernova type 1a. So while supernova type 2 are responsible for releasing most of the alpha elements, and supernova type 1a most of the ionic elements, and they have different lifetimes. So supernova type 2 have a much shorter lifetime, and therefore, if we form generations of stars and a component in a fast time scale, this means that we have supernova type 2 releasing lots of alpha elements, but we don't have time to wait for supernova type 1a to also balance these alpha elements with iron peak elements, and therefore we keep this alpha enhancement. So this means that basically the thick disks were among the first structures to form in these galaxies, and therefore they are very important because they trace the early stages of the formation and evolution of these galaxies, and this is mainly why we want to understand thick disks. So how can we form thick disks, in fact? So to explain these properties, so the fact that they're old, high velocity dispersion, low metallicities, alpha enhancement, there are mostly three main scenarios that were proposed in the literature, mostly theoretically, so with simulations. And one of them is the so-called born hot scenario. So the stars were formed in situ from a hot disk of gas, which was already dynamically hot, and from this thick disk of gas, we form stars, and we form a thick disk. This is happening in high redshift in principle, because we have said that the stars are all stars. But there is a second possibility in which the first disk that we form is not a thick disk, but it is a thinner disk that with time is actually dynamically heated to form a thicker disk. And this heating can happen in a slow way or in a fast way. So it can be a secular heating, or it can be a violent heating from, for example, measures. We are going back to this point in a second. But the third possibility is that we have accretion of stars. So direct accretion of stars from satellite, which require orbits that are typical of the thick disk, so more scattered orbits, and we form this thick disk, or at least more than most of the stars of the thick disk. So these are the three main ideas that were so far supported in the literature. So what do we know from observations? It's natural to think, okay, we want to study a structure which is old, so the natural thing to do, and even more now that we have a lot of GWST data, is to go to high redshift galaxies. So this is, for example, from a very recent paper which was posted in the archive last month, and here I'm showing there are images of galaxies from low redshift to high redshift, and you can see the difference. So at the low redshift, we have these thinner galaxies with more extended disks, and as we go to to higher redshift, we see like lower mass galaxies with these like thicker and smaller disks. So the main results they found, but they were also already proposed from in previous studies, and there were also like previous studies showing gas disks which were already thick also at high redshift, so everything is like matching together. So they found that only some galaxies have a double disk structure, and for example 10 years ago. Most of them show a single disk, and this single disk has actually properties more similar to the thick disks in galaxies with two disks. So we can say that these first disks, single disks, were actually thick. And there is also a transition to a double disk structure with a decreasing redshift. And this is happening in a downsizing fashion, in the sense that we see this happening earlier for higher mass galaxies and later for lower mass galaxies, which evolve like in a slower way. The important message to keep in mind here is that therefore the first disks were already thick, and this is basically a bit ruling out this scenario of the slow dynamical heating. Because in that case, we wouldn't observe something like this. So thick disks have high redshift, right? And this is very much supporting probably the in-situ Bornholm scenario, because we actually see disks that are already thick at high redshift. So this is what we have so far for galaxies at high redshift, and this is something relatively, we can say, new with all these GWST data. But for some decades, we have been analyzing very nearby galaxies in details. So to try to reconstruct, to do some archaeology and reconstruct the history of thick disks going to the past, right? So what do we know from these spectroscopic observations? I talk about spectroscopic observations because spectroscopy, you may know, allows us to accept the stellar populations, so ages, metallicity of the stars, and also the kinematics. So this is very important to reconstruct the history of these disks. Yeah, just a note about the definition. You remember that at the beginning I mentioned that for the first time the word the term thick disk was used to define something geometrical, so something that started to dominate from a certain height on. And this is actually the definition that will be used throughout the talk, and this is the definition which is mostly used in external galaxies. When they are seen adjoining the sky, we cannot do much more than defining a region which is dominated by the thin disk and the thick disk. So what we do is to take vertical surface brightness profile, which is, for example, these black dots. This is Z. And we use two different components to fit this profile. So we can see that one of the components is dominating in the midplane here. This is the midplane. And this is the thin disk here in the midplane region. But from a certain height on, we see that the second component is not to dominate. And this is the thick disk. So basically for us, the thin and the thick disk will be thin disk region in the midplane and thick disk above and below. Of course, the line, so the heights where the thick disk starts to dominate depends on the specific kinds. Yeah, so knowing this, what we can do, for example, with long slit, we can place two different slits, one in the midplane, probing the thin disk, and another one in the thick disk, so at larger heights where we know that the thick disk is already dominating. So there was a first pioneer series of papers from Yachin and Alcanton, which was very nice, analyzing spectroscopically for the first time thick disks. And they analyzed the structure, kinematics, and stellar populations, and they found that actually counter rotation was necessary to explain the kinematic properties of these, in particular of some of the thick disks. So for some galaxies, the counter rotation fraction was up to 50%. And of course, they were trying to find a common scenario for all the thick disks, and therefore they suggested that accretion was the preferred scenario. So all the thicks may form with accretion. Yeah, but a bit later it was shown that there was some diversity of properties. So for certain samples of galaxies, we can observe that there are different properties for different galaxies in the thick disks. And this also supports different formation scenarios for different galaxies, which depend on galaxy properties, and which can also suggest complex histories. So not only just one of the mechanisms that we have mentioned before. So this was very early studies with long slit, but you may know that with long slit we cannot provide vertical gradients, which is also important to understand how we form components. And we also cannot prove the transition region between the thin and the thick disk, which is something very important to understand how a galaxy can transition from a single disk to a double disk structure, something that I mentioned before. And so at this point, interactive spectroscopy started to provide some new insights on the thick disks. So now I will try to review a bit what we have so far in the literature from interactive spectroscopy in terms of thick disks. And we go back to the Hubble sequence. Here I cast the elliptical galaxies because they are not they don't have a prominent disk. So we'll try to take you from lenticular galaxies to the latest type galaxies to see what kind of thick disks they have and what properties and how we can understand a bit better their formation. So we will start with the lenticular galaxies, and I will first show you some results that from my PhD thesis some years ago already. So this is 3 lenticular galaxies in the Fornax galaxy cluster. This is the cluster, and this is the central galaxy of the cluster. These are the 3 galaxies, very nicely adjoined, and this is data from MUSE. This is deep MUSE data from the Fornax survey. So what I did here was to fit the spectra of I applied the Voronoi binning, special binning, and I fitted each one of these spectra with the PPXF. Some of you may be familiar with this, but it's a full spectral fitting technique. So it's basically fitting the full spectrum, as you can see here. So the black one is the observed spectrum, and the red one is the best fit. So what we need to give to PPXF, apart from the observed spectra, is a combination, well, a set of templates. And in this case, I used the Miles simple stellar population models with 2 different values of humanism over arm, because this is a property that we also want to measure for thick disks, because I mentioned before that this is quite important. And PPXF then gives you the best combination of these models. And from the weights given to these models, which corresponds each one of them, the combination of age, metallicity, and humanism over iron, we can reconstruct the stellar population properties. So it's a bit slow, I guess. It's not changing here. Okay, no. So yes, here I'm showing each one of the 3 galaxies. So each column is a different galaxy, and in the top row we have age, then metallicity, and then humanism over iron. I don't have much time to go into the details, but you can see that, well, first of all, the horizontal dashed lines are indicating the transition between the thin and the thick disk. So thin disk in the region of the midplane and thick disk above and below. You can already see that there are some differences, for example, in the colors between, the thin disk in these galaxies and the rest of thin disks. But yeah, this has to do with the position of these galaxies in the galaxy cluster, the galaxy cluster. If you want, we can discuss this a little bit more later. But let's focus now on the thick disks. You may see that there are similar colors in the 3 thick disks. So let's go a little bit more on the details of each one. So here we have age, blue colors, young ages of stars are red colors. And the 3 thick disks are basically old because we have red colors mostly, orangish colors. The 3 thick disks are also metal poor because we have blue colors, so low metallicity, and they are also alpha-enhanced because we see these high values in this color scale, which correspond to yellow, orange, and red colors. So basically, what we are finding here is the typical pattern that we would expect for thick disks, you remember, is in the Milky Way. So old, metal poor, and alpha-enhanced stars. However, when you accept the star formation history, which is something that you can also do with PPXF, because PPXF, so this technique basically gives you the weights given to the different SSP models. And therefore, you can extract the distribution of age, metallicity, and magnesium over iron. So what I'm showing here is the star formation history in terms of the mass fraction assigned to different ages. And I'm also color coding each age being according to the mechanism. So here I'm showing one of the galaxies, but we found a similar pattern for the three galaxies, so something qualitatively similar. So what we find here is that for very old ages, which means at very early times, we form the dominant component. So this is the thick disk, right? This is not the full galaxy. So we form this dominant component, which is most of the mass, with some chemical evolution. We see here some increasing in metallicity. But then when the star formation is more or less being quenched here around 9-10 gigayears, we see this additional component, which is younger, but it is also more metal poor. And then how can we explain this? The way we found to explain this is that these stars will actually form in a lower mass satellite. So because from the mass metallicity relation, we know that at the same time we form more metal-rich stars in galaxies which are more massive, and less massive galaxies, on the other hand, form lower metallicity stars. So at the same time, basically, we can form lower metallicity stars in lower mass galaxies. And this is why we proposed this component was actually accreted. So basically what we find in these three galaxies is that we have in the thick disks, we have a main population which is older and metal poor than the disk, for example. And with this younger contribution which is more metal poor. And this points to a combination of an in-situ and ex-situ formation of this. So if you remember, I mentioned these three scenarios. The first one was in-situ, the last one was accretion. And here we have a main in-situ formation scenarios with some stars that are from the accretion. That come from accretion. So we propose here a complex formation and evolution for these activities, not coming from only one of these scenarios, but a combination of them. I have to say this was not these were not the first lenticular galaxy to be analyzed. There was an earlier study from Sebastián Comerón et al. 2016, in which they use also Muse data to analyze one lenticular galaxy also in a galaxy cluster. They found something similar to what we found in one of our galaxies, with very old ages basically everywhere, with some differences in metallicity. But unfortunately, they didn't extract the mechanism of iron abundance and the star formation history. Yeah, so this is basically what we have for lenticular galaxies. But let's continue our journey to the right side of the Hubble system. So let's move to spiral galaxies, later galaxies. Do we also find this same information scenario? Do we also find the same properties, or metal poor athanasic disks with some potentially accreted components? So the very first study of thick disks with interactive spectroscopy was actually not done with Muse, but with VMOS. This was 2015. This was also a paper from Sebastián Comerón et al. And this is a galaxy which is, not entirely clear what type it is. Some emission lines, but it was classified as an S0 or an NC galaxy. The important thing is that it shows also, you can see here on the left age and on the right metallicity. So the green horizontal lines mark the separation between the thin and the thick disk. And you can see the low spatial resolution with only one Voronoi beam in the thick disk. But they were still capable of showing that this thick disk was actually very old and also metal. Again, here we found a similar patterns of an old metal poor thick disk. And again, unfortunately, we don't have the alpha announcement for this galaxy. So let's move to another spiral galaxy. This is a massive SP galaxy that we analyzed with Matik, who led this work, and we had for this galaxy these two Muse pointings covering only part of one side of the disk. And with a similar approach, so again with PBXF, in this case we had plenty of emission lines, and we had to also fit the emission lines to then fit the absorption spectra. And we extracted the stellar populations again, and we found this kind of maps that we can compare with this map if we want to locate where the thick disk is dominated. So the thick disk is actually this red region here, which if we compare this map on the right with the maps on the left side, this is age, metallicity, magnesium of Orion. So the thick disk is basically this red, so very old, metal poor and enhanced structure here. While the thin disk is much younger, metal rich, and closer to solar values in terms of enhancement. So again, we find a similar pattern. We are finding, it seems like all the galaxies have this pattern of old, metal poor, and enhanced thick disk. And we also extracted the star formation history, again, in a similar way. But again, we found that there is a dominant, very, very old component in the thick disk, and this little one here, a bit younger. It is like lower mass than what we found in the other lenticular galaxies, but it's still there. And we also analyzed the metallicity and age distribution of these stars. So this is basically the same star formation history. This is age, and here we have metallicity. So separated for different metallicities. We see that this dominant component actually is this one. So goes from a poor to metal-rich stars, especially when we go to younger ages, which is what we would expect. But then for ages between 8 and 10 gigayears, we see this bimodality in metallicity. So we actually see that there is this tail of the main population, but there is this other additional population, which is much more metal poor. And again, the way to explain this is that these stars, or the gas which form these stars, has to come from outside, from a lower mass satellite. So yeah, looks like we have found a similar scenario for lenticular galaxies, for this spiral galaxy, which is very, very massive. So let's see if we find this actually for all galaxies. Is this the standard pattern of formation for thick disks or not? So now I will show you a sample of very different galaxies. This is a sample that was analyzed by my former student at the University of Heidelberg. This was her master thesis. Her name is Natasha Sattler. Now she's working at the University of Heidelberg during her PhD with Katrin Krekel in other things like gas science, still galaxy evolution anyways. And so she analyzed a sample of 8 adjunct galaxies that were released. This is also Muse data that were released by Coleman and al. In 2019. 5 of these galaxies actually have a distinct structure of a thin and a thickness. So I'm going to focus on these 5 just for the sake of time. So we are kind of moving again towards the rightmost side of the Hubble sequence. So yeah, this is work which we have recently submitted, and is also in the archive. If you're curious, I can give you the reference, or yeah, and you can check the link. So what are we analyzing here? Very different type of galaxies. They are very dusty. They are star forming. You can see these already from the images. They are like more irregular in their John view, and they have lower masses, and they also have extra corona diffuse ionized gas. And this means that they have ionized gas also in the thick disk region. This sample is located here. So this is the diagram of star formation rates as function of the galaxy mass. And just to give you a reference, I put here the 3 lenticular galaxies. So I don't have the star formation rate, but they are quiescent galaxies. They don't have star formation, but they had like a range of masses more or less here. So similar, kind of similar masses to these galaxies that I'm showing now. However, very different star formation rates because these galaxies are strongly star forming. And the other, you remember the last very massive spiral galaxy that I showed, AGC 5746, is located here. So it is a green valley galaxy, so not so actively forming stars, let's say, and it is very massive. So very different range of masses from what we are talking about now. If you remember at the beginning, I said that when we move to the right in the Hubble sequence, we tend to have lower mass galaxies and higher star formation rate, so mostly higher, stronger star formation. So this sample was analyzed kinematically by Comeron et al. They published this data in 2019, and they showed that the kinematics doesn't need any fraction of counter-rotating material to explain this results. So they proposed an internal formation of these thick disks, although compatible with some accreted material. So let's see what we find from the stellar populations. First of all, sorry for changing so much the color scale. This is how I have the results, but I can understand that it's confusing to have blue, red, and green, and so on. And now we have a different color scale. But if you pay attention to the numbers, we have a color scale now from 0 to 6 gigayears. So we are basically talking about very much younger galaxies than what we have seen before. Just to, I don't know if you noticed that, but the thick disk of the galaxies that I showed so far were more or less 10, 12 gigayears old, so much older than these galaxies. So in each column we have a different galaxy, and we have in the top panels the age, in the bottom panels the metallicity. So the first thing that we can see in this sample is that we have very young ages. These thin disks are very young. Again, the horizontal lines indicate the transition between the thin and the thick disk. And the thick disks actually have like ages around 4-5 gigayears, which is basically the age of the thin disks of the galaxy that I previously shown. So we are talking about relatively young thick disks, basically. So much younger than the more quiescent galaxies that I showed before. And regarding metallicity, we are talking about mostly subsolar values and much lower metallicities than what we found in lenticular galaxies, and in that also a very massive disk-dominated galaxy, which was AGC 57. So completely different scenario and picture and types of galaxies. So for the first time, we are finding kind of relatively young thick disks, which is a bit, if you want, challenging this first idea of finding always an old thick disk. And in terms of star formation history, if we now extend the star formation histories of the thick disks, we see that this is also very different pictures from what we have found before. If you remember, we had star formation histories that were something like this. So they had a very strong component here at very old ages, and the star formation was basically the star formation history was basically truncated here at 8 gigayears, which is now when these galaxies are basically forming most of their stars in the thick disks. And another very important thing is that these star formation histories are extended. So they actually extend to very recent times. So this means that we are forming stars in thick disks also at very recent times, which is also something probably unexpected and new. But remember, I told you that these galaxies have also some ionized gas at the height of the thick disk. So this is what we have found basically in very later galaxies, suggesting that we have a thick disk formation which happens slowly in situ, but now slowly, so in an extended way. So far I showed you small samples, individual galaxies. We have in total 15 galaxies with the stellar populations. I didn't show all of them. And we do not have, or we didn't have so far a comprehensive and systematic study of thick disks in different types of galaxies, because observations are very challenging. We need long integration times because thick disks are faint, and to do stellar populations, we need very deep data. So at this point, basically, we actually need a systematic study of a larger sample of thick disks. And this is one new survey, which is called GECOS, comes into this game. And the survey is targeting 35 galaxies, giant galaxies, which are Milky Way-mass, and it is providing deep Muse data, which are ideal for the study of thick disks, because again, we need to reach a central synatomize to understand the stellar populations. So just to connect the samples that I showed so far, the GECOS sample is located here. So we have masses that are around the mass of the Milky Way, which should be more or less here. And we have a wide range of different star formation rates. So this is basically ideal to study trends with the star formation rates, having removed the dependence with the mass, which is another important factor that can be affecting the properties of the thick disks and the galaxy in general. So this is the same diagram, but in a different way, just to show that, the sample basically has different star formation rates, and we have galaxies in the star formation main sequence, but also above and below. And now I'm going to show you the first results from the GECOS survey in terms of the stellar population of the thick disks. So I will show a subsample of 6 galaxies, which are the 6 galaxies with clearly distinct thick and thin disks. We know this from a previous morphological decomposition from the ES4G team. Among the first 11 galaxies of the first internal data release of GECOS, that was just the first subsample of galaxies fully reduced and ready to be analyzed. So to analyze these galaxies, which are also located in different locations with respect to the star formation main sequence, which allows us to start to investigate some trends with the star formation rate. So for this analysis, I used the new NGIST pipeline, which is an updated version of the modular GIST pipeline. You may have heard about this. It was from Adrian Bittner in 2019. So we have developed like a new version, a bit improved version and updated. This is using also PPXF, and in this case, I'm using SMILES models because these are new models that can cover also different values of magnesium around instead of only 2 values. And these are the maps that I obtained. Different galaxies are in different columns again, and I ordered galaxies with increasing star formation rates to the right side. Again, we have age, metallicity, magnesium over iron. Sorry again for the change of the color scale. However, in my defense, I can say that I like very much this scale for the age, because it helps a lot your eye to detect what is old, what is young. So magenta colors are old stars, and cyan colors are young stars. So from a first glance, you can actually see that all the ages are located on the left side when we have more quiescent galaxies, so lower star formation rates. And on the right side, we tend to have more cyan colors. Yeah. And this happens both in the thin disk, see here, and in the thick disk. And actually, the thick disk in the right side, remember a bit this last sample of very late type galaxies from Natasha, my student that I showed you, where we actually have young stars also in the thick disks, while the thick disk on the left side, hosted by more quiescent galaxies, tend to be like the typical old metal poor and alpha enhanced thick disks. Yeah, metallicities are also very dependent on the star formation rate. just qualitatively, the highest metallicities are found in the thin disks of the more quiescent galaxies. And and again, the most alpha-enhanced thick disks are located also in the more quiescent. This qualitative, but we can also kind of quantify this. So this is these properties as function of the subformation rates. And in fact, so from the left to right, we have age, metallicity, and magnesium over iron. Metallicity doesn't show any clear trends. However, the galaxies that are more quiescent, so with a lower subformation rate, tend to have these properties we saw at the beginning, lenticular galaxy, this other massive galaxy, which had very old and alpha-enhanced thickness. While again, the galaxies that are more self-forming with these high subformation rates have younger and resonance thicknesses. So basically, this sample, this investigation of the trends with the subformation rate also supports the idea that more quiescent galaxies have had in the past like a faster evolution, and therefore they formed the thick disk with a fast formation in high redshift. But on the other hand, the galaxies that are forming at the moment had a slow evolution in the past, and they had also a slow extended formation for their thick disks. Good. So I'm not sure if, how much time do I have, but
You have 5 minutes.
okay, 5 minutes. Yeah, then I will go fast with this. I wanted to show you one single disk galaxy because we have talked quite a lot now of galaxies with a double disk structure, but the galaxy with a single disk in the local universe, a very nearby universe, also exist, and they are very important because they can help us to understand the transition between the thick disk formation and the thick disk formation and the thin disk formation. And just very quickly, this was we have more of this galaxy, but I wanted to show you this like a representative example. It was the bachelor thesis of the same student, Natasha. She analyzed one of those single disk and spiral galaxies. And therefore, for a single disk galaxy, you would not expect clear differences in the stellar populations, right? But on the other hand, when she extracted the stuff from the stellar populations, she actually found structures. And she found this is just a metallicity map very quickly. So she found that this galaxy, which is in general are young, and the metal pool, which is what you'd expect for a very late type galaxy. This is a galaxy with plenty of dust and gas and star formation and so on. But this galaxy basically has a thicker metal core structure, but also an inner metal-rich thin disk, which is forming here. So the question here would be, are we witnessing the first stages of the formation of a future thin disk, which is just growing inside out? So this might be, and this is also much very well what we have said so far, that lower mass and very late type galaxies evolve like in a slower way, and actually these galaxies basically at an early stage in which it hasn't formed yet the fully, the thin disk. So the last thing I would like to show you is a comparison with some simulations. I will try to also go a bit fast here because we are already a bit late. So we have seen that we have limited samples, we have individual galaxies. We don't have, this comprehensive sample that can allow us to investigate trends with the mass, with star formation rates. Because for the full gecko sample, we have to wait a little bit more to have the 35 galaxies. But in the meantime, we can also analyze simulations, because in simulations, we can have large samples, and we can also travel to the past in the sense we can go back in time and see what actually happened in these galaxies. So I used a sample of 24 galaxies from the AURIGA zooming cosmological simulations, which are Milky Way-mass, relatively isolated at redshift 0. And I tried to use a similar approach, an approach as similar as possible to observations. So I projected the simulations edge on as well. And I also decomposed their vertical surface brightness profiles into thick and thin disks so that we can treat the thin and thick disks with the same definitions we used for observations. And I actually started the projected stellar population maps with age, metallicity, and magnesium overlap. We have 24 galaxies, but I'm going to focus only on 2 of them. Yeah, which are like the most extreme cases and the most representative ones. So I picked here one galaxy in the bottom panels with the typical thickness that we would expect. Again, old, metal poor, alpha NAS. And another case, which is one of the young, relatively young, and thick disk with not so clear, not so sharp differences in the chemical properties with the thinness. So in simulations, we do have the opportunity to see, to go back in time and to see why do we have these differences in the properties, what happened in the past to get these differences, to give these differences. So one of the things that we can do is to plot these different snapshots. Here I'm showing the surface brightness just to give you an idea of the morphology of the galaxy. And on the right side, I'm showing the metallicity maps for different redshift, different snapshots of the simulation. So this galaxy, high redshift, has very low mass. So here, which is more or less 10 gigayears ago, we have a small kind of thick structure which is already rotating, which can be considered basically a primordial thick disk, if you want. But it is still very small. And from the time on, in the subsequent snapshots, we see the effect of the merger. You can see here there is a small satellite. And the disky shape is basically disturbed. And we cannot form any thin disk until very recent times. So basically the merger ends here, which is quite a massive merger. I'm going back to this in a second. And finally, we have the formation of the thin disk only, in the last probably 3 gigayears, which is something peculiar. And we can say that also because if we compare to another galaxy, which is probably the case of the most typical or prototypical thick disk, we see that this galaxy is very different. So the history is completely different, and especially from high redshift snapshots, you can see that when this galaxy was really low mass, this other galaxy is very massive. This had already half of the final mass, and it had already a fully developed thick disk, and there is also a thin disk which is increasing its metallicity and growing then later on during the evolution of the galaxy. But the galaxy is basically there already 10 gigayears ago. We are talking about a redshift of 1.7. So this is one of the key things that we can consider to understand why these galaxies are different. So the mass and the very early evolution, but also in simulations we can quantify the amount of accreted stars, and we see that the massive merger in the galaxy on the left actually provided 50% of the stars in the thickness. So half of the thickness is ex-situ and the other half is in-situ. And more important, this satellite galaxy also provided a lot of accreted gas to fuel the late star formation also at the heights of the thick disk. And therefore, this ends up in a young, relatively young thin disk we have seen in the maps. The other galaxy, has some mergers, but only 7% of the mass of the thick disk. And this is also because this galaxy was already massive here. So here we are talking about mass fractions. So basically mergers also had a lower impact in this galaxy, right? So this is probably suggesting, just to reconnect with the observations, this is probably suggesting that gas accretion is the key to understand why we have extended star formation also in this relatively young thick disk. And actually, I didn't have time to mention this, but other studies of the same sample, for example, that sample of galaxies that were a very late type, Roche et al. In 2022 analyzed the gas properties, and they found signs of gas accretion in this type of galaxy. So this could be also the way to understand why we have young disks in some star-forming galaxies. And this is all I wanted to say. So just my take-home messages. In general, I think these we have seen they are complex. They result from the interplay of different mechanisms and processes. But we have seen that in common they have like a main in-situ formation in most galaxies, and the later growth that can happen with the accretion of stars, but also gas and later star formation. And we have seen also some diversity, especially in observations. I think it's a different galaxies with different masses and star formation rates. And not all the thick disks have to be necessarily old. We have seen some relatively young thick disks. This means that we may have different formation histories in quiescent galaxies and early fast formation and high redshift, but then in star forming galaxies lower and extended formation with Thank you very much.
Thank you, Francesca. Questions? Horacio? Students? Michele, and then Mark.
Thank you very much for your talk. I wonder that you didn't mention the membership. Actually, if the galaxy you analyze it and it's isolated one member, dense cluster.
Yeah, that's a very good question.
At the beginning, very beginning.
Yeah, so the first sample that I showed, the 3 lenticular galaxies that I showed at the beginning are in the Fornax cluster. And then moreover, they are in different positions from the cluster center. However, they show differences between them in the thin disk, which was formed later, but not in the thick disk, which was probably formed even before these galaxies fell into the cluster. So according to the ages of the thick disk, they would actually form before these galaxies enter into the cluster. And because we know this from other studies simply. And furthermore, one of the galaxies, the one that I mentioned that it had a very old thick disk, but also an old thin disk, this one was probably part of a preliminary subgroup. Before entering the cluster, it was part of a group that fell into the cluster altogether. And this could be the reason why we also have an old thin disk, because this galaxy was pre-processed even before entering the cluster. And in the case, we have this pre-processing before entering the cluster. But yeah, in principle, we don't see that, for example, the 3 thick disks have differences depending on the distances from the cluster center. And I'm saying this because they are very, very different locations in the cluster center. One of them is actually relatively far away, if you want, from the center, and another one is in the core. And they have differences in the thin disk and not in the thick disk. So I think this is a very important point. However, I'm not sure if thick disks that were formed at very early times were affected by the environment. They would probably form before entering the classes or group, and therefore, well, this kind of things could be key to understand, for example, thin disks, because they get their gas stripped, or they suffer from any kind of interactions. I'm not sure this is also affecting very much the thickness. And this, for the rest of galaxies, they were isolated.
Did you compare with
Last one.
We can chat later.
Okay.
About it.
So now Michele and then Mark.
And I saw that you said that
Exactly.
don't know if but I would like to know
So it's actually non-parametric. Yeah, because PPXF doesn't know what is 12 years or two or yeah. You just give the SSPs and then it gives way to the spectrum. Yeah.
Mark?
Yeah, so I wanted to know the galaxy distribution in terms of the N and then the P is consistent for the alpha and the abundance ratio, which is normally used to demonstrate the distribution.
Sorry, can you repeat the question? That I'm not sure I actually understood. Yeah, the alpha enhancement.
What I'm trying to understand is the alpha element and the ion ratio, the abundance ratio, has to versus either oxygen or nitrogen ratio.
You mean other abundances? No, no, because in the stellar population models they use, we only have varying magnesium over iron. Yeah, we could use other techniques to measure other abundances. Thanks. Yeah,
Thanks for the very nice talk. Actually, I do have two questions. I'm going to ask the last one first. That is from your previous slide. You showed that there are basically two possibilities to form these thin and thick these structures. I would like to know if you have tried to find out which one of those is more like the one that is driving most of those disks from simulations.
Yeah, I don't think I have a clear answer for this because so here I'm showing the two extreme cases and they look like very clear, but then when you look at the rest of the sample, they are not so. I mean, it's difficult to divide the sample into one group and the other group because they are in the middle. Yeah, exactly. Yeah, I think, yeah, that's basically the answer, I guess. Yeah, there are probably 4 or 5 galaxies with this clear history and structure like this galaxy, with this very clear old metal poor and alpha enhanced thick disk. But also, yeah, we have to be a bit careful with yeah, it's a distribution. I want to say that we have to be a bit careful with comparison of simulations with observations.
Later.
Yeah, so we have very few new studies from JWST data. I showed something at the beginning. This is basically what we have so far at high redshift. About the compactness, I don't think we have an answer. Probably you will give an answer to this question because I know about your work. But yeah, I don't think we have spectroscopy for that kind of galaxies, but it would be certainly very, very interesting to know that. Should, yeah, do some spectroscopy of your galaxies.
More questions from the students? Remember, there is the Google Doc you can write. If not, we can have one more from Horacio.
I'm sorry. The following question was if you have compared with the industries.
No.
There should be something about the influence of the environment.
Yeah, not yet. Yeah, I have a project with Annalisa in common. We want to actually do that because, of course, the limitation of these simulations is that we don't have the cosmological context and also that they are all Milky Way-mass. So with TNG50, for example, we want to analyze a larger sample of galaxies with different masses And especially we want to understand what is the role of environment in this in the thick disks. Yeah, so not yet.
Marina? No. One more from the students? Go ahead.
C'è a primera pregunta que le hizo por Pina.
Vai, Marina.
Thank you for the very much talk. So as far as understood, that these galaxies in simulation, they're all Milky Way size galaxies, right? So they are
Milky Way-mass.
Milky Way-mass.
Mhm.
But how about the bulge? I think it's the kind of the same line as her question. I wonder if the bulge is large, maybe stabilize the potential of the galaxy, and so the growth of the thickness could be different. So have you looked at the size of the bulge and of the galaxy?
Yeah, so these simulations, I have to say, they are not characterized by very prominent classical bulges, but most of them, they have bars and box peanut bulges. I didn't find any trend between, the size of these box peanut bulges and the properties of the thick disk. I have to say I didn't, focus too much on this. Maybe, yeah, this is an analysis that could be done a little bit more into the details, but I had a look and I didn't find easily any trend. Yeah.
Rogério.
So, from your first maps you were showing for the first galaxies, I noticed that somehow a age metallicity degeneracy is showing up, like you have higher metallicity in the center, lower ages the reverse. Lower ages in the center and higher metallicity for at least for one galaxy. So have you tried to test this effect, like perturbating the spectrum and trying to fit again to see if you can remove this degeneracy somehow?
You mean something like Monte Carlo simulations?
Yes.
Yes, we did. You mean this sample, right?
Yeah.
So I didn't get very much what you were referring to.
Lower ages in the center,
Yes.
and you have higher metallicities also in the center for the very right one.
Yes.
Like this is somehow a signal of age metallicity degeneracy.
Well, here we have a nuclear star cluster in this galaxy and in this galaxy, and we interpreted this blob here as the nuclear star cluster like spread by the PSF. So in principle, we always thought that this was actually real. Yeah, but you never know how the degeneracy is still there, even with full spectral splitting, and you never know.
It's very metal rich.
It's very metal rich, and
Also,
it's also one.
I have a few questions, but we can ask over coffee. I'll just ask one. So in the plots for the S0, for the Fornax 3D sample, you showed two metal core populations with age differences, right? Or did I
Yes.
get that wrong? Okay.
Yes, I guess.
What is the difference in the metallicity decks, and how sure are you this difference is real and not just a continuum?
Yeah, so I guess we are talking about the
Yes.
difference between this population and this population, right?
Yes.
So here we perform Monte Carlo simulations, and we got different errors in metallicity, which were about 0.1 decks. So this difference would be, as you can see here, larger than the errors that we got. This was one of the questions, but it was another point, I think.
Yeah, if they were
Yeah.
related, if it was real.
So
Okay.
in principle, we are confident that the difference that we see, it's real. Although going back to the degeneracy, well, we have still to,
And if I made the last one, what is the environment of the single disk galaxy?
the single disk galaxy is an isolated galaxy, but with this I don't mean a fully isolated galaxy. There is a companion and some signs of gas accretion, but it is like a bit far away, but yeah. So it's not part of the group of that, but it's a companion.
And before we all get very tired of the heat, I just see everyone doing like this. Let's thank Francesca again. We have to report being broken. Vice Chef of Department, not yet, but you were elected.
But please,